and I can always talk into this. I don't think you need that. Don't want to do that. Okay, someone has started the recording. I don't know who did, but perfect. It's fine. Right. So wait. Hide it off the screen. Right, we'll start in a minute or two. Let's see if I can fix this first, though. Perfect. So then I can do this. Check this. Yeah, the whole thing. Oh my word. Perfect. Okay. All right. I suppose we might as well get started. Okay. Hello, everyone. Welcome to the final exam crash course for ELEC3114. I just want to go through a couple of announcements at the start. I uploaded a PDF that had the major notes that I thought were important from the last half of lectures. So that's stuff like the root locus plots and whatnot. So feel free to look at those. They're not fully exhaustive, but they're just the main sort of things that I thought might be relevant for your exam. Okay, and I thought it'd probably be best if we just went through a past paper. This was last year's past paper, so I actually haven't seen all of these questions, but hopefully together we should be able to get through them. Please feel free at any time, stop me asking any questions, and I'll happily go over it. Okay, as a lucky person here, you can stop me at any time and ask any questions. Okay, so the first question we've got here, we've got this block diagram, and we asked for find the state space representation of the system. Okay. All right, cool. Yep. Keep inviting people to the chat. That's not a problem at all. Okay. Now, I don't know how familiar people are seeing question. Anything? No, you're all good. It's fine. I don't know how familiar people are at seeing this sort of format before. All right. Where you've got these 1 on S blocks all over the place. Have you seen many of those in lectures? Yeah. What are you thinking the first step would be? Well, where would you start? Yeah.
I would start at the input and output because you definitely know what you're trying.
Yep, that's fair enough. All right, you know exactly what this is and what this is. Okay. Yeah, that's a great point to start from. Okay. I like to start by looking at this and going, I've got an S block, so this is going to become my X double dot. And then this will be X dot, and this will be X. All right. And then I can say that this is, say, X1, and then this can be essentially X2, and so this will be X2 dot. Does that make sense? So we're using those derivative blocks or the integral blocks to our advantage there. And so then if I wanted to find an equation for X2, not double dot, X2 dot, we say it's going to be equal to 10 u of t plus X2, well, not plus, minus X2a minus x1 times 4. That makes sense? Cool, cool. Yep. And then if we want to get a y of t, our y of t is equal to 2x1 minus 4x2. Okay, and now we wanted to find a state space representation. And we also know that x1 dot is equal to x2 because, well, that's what we set up here. Make sense? Cool. So from there, I'm going to have my x1, x2 dot is equal to this representation of x1, x2 plus u. There you go. And then we're going to have y is equal to x1, x2. All right, because we have no d. That makes sense? And then we just fill it in, which is just going to be 0, 1. And now this is going to be x1, so it's going to be minus 4 minus a, 0, 10, and then 2 minus 4. Okay, happy with that? And essentially, it's, as it's worth, about 4 marks. This is about 2 marks to get all this. And then 1 mark for that, 1 mark for that. Okay. So hopefully that should be, the trickiest part is definitely this part. Making sure you remember to do this. All right, 1, 2, 3. You do that part, and then most of it should just be derivating the equations. Happy with that? As I said, please stop me at any time. Any questions or anything? Okay, determine the value of alpha such that the system is marginally stable, and then find the natural frequency of oscillation. All right, so question 1.2, we want marginally stable. Now, what do we need for a system to be marginally stable? Love an answer in the chat, or if you want to answer, that's okay. That's okay. Because, well, there's essentially, if we think of our PZ, like our pole map, right? Look at our poles. If I have a pole here, is it stable or unstable? Unstable. All right, so this is unstable. What about on this side? Stable. Very good. What about this spot right here? It's marginally stable. There we go. All right. Proof by trial and error. So the important thing for this question is, well, we know that anywhere on that line is marginally stable, which then means that there are 2 conditions that can be met for a system to be marginally stable. From there, what do you think the 2 conditions would be? Yep, poles all imaginary. Or pole at origin. That make sense? So, with that understanding, we then want to go, okay, we need to figure out where our poles are. So naturally, we need to do the eigenvalue of our A matrix, which is equal to the determinant of Si minus A, which is going to give us the determinant of S minus 1 for s plus a, which will give you s of s squared plus as plus 4. All right. Then from there, we can say, well, we want it to be either, we can't make this at the origin, it's just impossible, okay? So the other condition is we say if alpha is equal to 0, because then we would have s squared plus 4, which gets you s plus or minus 2j. Make sense? Cool. And then the oscillations occur at 2 mega. Or 2, well, it's not really a mega, is it? It's just rads. Rads per second. Okay? Which is tying into this 2 right here. Make sense?
Yo.
Hello, welcome.
Okay.
Yeah, that's good. We have just started going through the 2021 past paper. So feel free to ask me any questions anytime. Okay. Is that clear with everyone, how I went about solving that? Chat is very quiet today. Well, I'm just going to assume it is, unless someone wants to jump in. Okay, so assume alpha to be still unknown. Find a condition on alpha for the system to be controllable and observable. Confirm that the value of alpha from question 1.2 satisfies the controllability and observability conditions. All right. So, what is the equation that we need for a matrix to be controllable? It should be, that's observable. So we have B and AB, which will then go to A squared, B, and whatnot, right? For the controllability. The observability one is the one that you're thinking of, which is C, CA, and whatnot. The trick is you sort of just look in the format going, what does it mean for a system to be observable? And it means that we can see what the final values are, right? We can see what the final states are, which is how it relates to C. Whilst for a system to be controllable, we have to be able to send signals to that system. If you think of it as, if I had an A matrix that was 0, 0, 0, and my B matrix there was 0, can you control that? Not really. It goes to 0 and it stays at 0. You can't put it wherever you want. Does that make sense? You can say no. That makes sense? All right, cool. That's fine. So we have our B matrix that we got from above, right, which is B is equal to 0, 10. Our A matrix is up there of 0, 1, minus 4, minus A. Yeah. Cool, 1, minus 4, minus A. And then our C matrix, which is 2, minus 4. Okay, so for our system to be controllable, it's just going to be 0, 10 for the first one, and then 0 times 0. We just have to times these two together, so 0, 10 gets you, oh my word, what am I doing? It's the other way around. You see how like the matrices didn't line up? I probably didn't do that quickly, but like you see how A has to come first? Because it's always tricky to remember if it's AB or BA. we try and do it the other way, it just doesn't work. So I need 0, 10 here. So then that becomes 10 there, and then 0 minus 10 alpha. Cool. So the controllability matrix is equal to 10 minus 10 alpha. The observability matrix is equal to 2 minus 4. And then 2 minus 4 here, which is going to be minus 8. And then 2 plus 4 alpha. Okay, so are these two matrices controllable, or controllable and observable? How do you know? Perfect. All right. We want to see, can I get away with using just this guy or just one of the columns? And we can see that, well, no, we can't. We can't replicate this in that line. We can't replicate this in that line. That's the trick that you use. You're right, we do check rank, but often it can be like, if we're in the middle of exam, it can be quite tedious to try and figure out whether the rank is that. You can almost sort of do like a cheap way of going, well, you know that the rank isn't going to be less than that, because you can see you can't replicate it anywhere else. That make sense? I'm mentioning this because Arash is a bit notorious for putting in questions where a quick little trick will save you 20 to 30 minutes. Okay? Because otherwise you can go through all the hard work, but if you don't notice the trick, it's going to come back at you. And considering he has 12 marks in there as bonus, I'm going to guess there's going to be more and more of that. Okay? So if the question looks really long and really tedious, it might be because you're missing something. And it could just be a multiplying through by 0 or something. I'm just making that comment now before I forget. Okay, but we had to check these for when alpha was 0. So then that just becomes the controllability matrix is going to be 0, 10, 10, 0. And then the observability matrix is equal to 2 minus 4 minus 8, 2, which is still, different. All right, and that is question 3. Make sense? All right, now we get to a bigger question, which is use the values of alpha from question 1.2 to design a state feedback controller in the forms of ut is equal to minus kx plus r of t, where k is equal to k1, k2, plus zeta is equal to 0.8, omega d is equal to 6 radians per second, to a unit step reference signal, find the steady state error ESS due to a unit step reference signal. Doesn't this seem familiar? Okay. This is going to be a lot of work, but that's okay. So scroll, just keep going across. That's going to be a solution to the problem. So we know that we have the values for zeta is equal to 0.8 and omega d is equal to 6. So that omega n is equal to omega d on the square root of 1 minus zeta squared. I believe you get a formula sheet.
Yeah.
Yeah. Yeah, so my guess is that'll be on the formula sheet. I don't know for certain, but that'd be my guess. Okay, so then omega n here is equal to 10. All right, when you plug it all in. And we also know that the pole locations for this, S of 1 and 2, is equal to minus zeta omega n plus or minus j omega n square root of 1 minus omega n 1 minus zeta squared. Does that seem familiar to everyone? Cool, cool. It's been a while since I've done some of these questions. Hello, welcome, come on in. All right, so this basically gives you minus 8 plus or minus 6j. Okay. So the important thing from there is now that we have that, we can go, okay, we know that's where we want our poles to be at the end. Okay? And so the important thing is, how can we get our poles there? So we are going to need to have it so that the determinant of our SI minus AB, or A minus BK, leads us to be effectively equivalent to S plus 8 plus J, or 6J, and then S plus 8 minus 6J. Okay? All right, and we know that K is equal to K1, K2. Okay, and so now we just have the lovely fun task of breaking this down into 0, 1, minus 4, 0, minus 0, 10, K1, K2. Okay, and then we take that, all right, which we're just going to see here is going to become 0, 0, 10, K1, 10, K2, right? 9 times out of 10, one of these values will be 0. Okay? You can almost guarantee it. Okay? I haven't seen a single one where it didn't have 0. Okay? The observer's a bit different, but like, this is the sort of thing where he's like, he likes to do this to make your whole life a little bit easier. Okay? So you go through all this and you'll eventually end up getting S squared plus 16S plus 100. Well, this side anyway will be that. And so therefore you will end up with the determinant of S minus 1, and then what's this going to be? 4 plus 10K, 1, and then minus of 0, minus of minus plus 10K2, S plus 10K2. Which becomes S squared plus 10K2S plus 4 plus 10K1 is equal to S squared plus 16S plus 100. And you have the fun task of just matching patterns, of saying 10, well, I'm just going to leave it all in one color, screw it. 10K2 is equal to 16, so therefore K2 is equal to 1.6. Yes. And then 4 plus 10K1 is equal to 100, so therefore K1 is equal to 9.6. Okay, makes sense? Now, we're not finished. We need to find that steady state value. Steady state error. Okay, and so therefore we have the E of S is equal to 1 minus T of naught, okay, which is the DC gain. Alright, so that'll be T of naught is equal to C of minus A minus BK inverse B, where we set the SI, or we set the S value to be 0, because otherwise there'd be an SI here. That makes sense? And so that would become, since we know that C is equal to 2 minus 4, then the A minus BK, we can sort of replace with what we know that 4 plus 10K is going to be 100, and 16K2 is going to be 16. So it just becomes 0 minus 1, 100, and 16. And we're taking the inverse of that and then multiplying it by 0, 10. Okay, and now you see here how the top one is 0, so we really don't care what the top is. Okay, like if I have A, B, C, and D, and I'm multiplying that by 0, 10, all I'm going to left with is 10B, 10D. Does that make sense? Because of that 0. So therefore, when I have this and this, when I take the inverse, I don't care what's in that spot. All I will care about is what the determinant is and what's at B and what's at D. Okay, that makes sense? Okay. Luckily for this one, it's straightforward anyway, but it's just me trying to show you if there's ways to make life a little bit easier, we want to take it. And so like the determinant will be, it's this times by that, so it's going to be 100. So it's going to become 2 minus 4 on don't care. And this is going to be 1, and that swaps over, that's 0. And that's over 100. 0 and 10. Cool. And therefore we're going to end up with still don't care. And then that's going to become minus 4 and 0 over 100. 0 and 10. Did I make a mistake somewhere? Perhaps I did. So we will do that one first, which would get it to be 0 and 10, 0 and 0. And so you become 2 minus 4. That should be 1 on 10. 0. Yep, there we go. That's what I wanted. And then that gets me 0.2. That's my final answer. That make sense? So you see, I didn't even bother with those don't cares. Honestly, didn't impact the answer. So then the error steady state is equal to 1 minus 0.2, which is equal to 0.8. All right. And that's the final answer you want. Any questions with that? Feel free to ask. It's fine.
Could you do so what did you check? You just multiplied?
Which part?
With the... so how did you work out where the don't cares were?
Okay, yes. Yes, so that came from this guy. So because there was a 0 here, all right, I'll put it on the side here. We have essentially, we're going to have A, B, C, or D, all right, that we could have. And if I have 0 and X, then I'm going to end up with A times 0 times B times X. And then C times 0, D times X. So you see how the values of A and C don't appear in the answer. And so as a result, that's why I consider them as don't cares, because they're just going to disappear.
Okay.
You can expand it out like normal. That's not an issue at all. All right. And for you, if that's easier for you, then do it. That's fine. Most of the time, if it's like a 2 by 2, it's fine. All right. It's not really an issue. It's when you get to stuff where you have like, you have to say A, B, C, D, E, F, G, H, I, and they say take the inverse of that, and you're like, oh, that's not going to be fun. But then you're multiplying it through by a matrix which is 0, 0, 1. You're going, oh well, I really only care about whatever ends up in that last column. So 6 values I don't need to worry about calculating. But it is important to remember the determinant, because that's still dividing on the bottom. That make sense? Yeah. So for simple questions, it's much to niceness, right? You can, especially when it's like just you swap numbers over and you change it from positive to negative, not really an issue. As soon as you get to like a 3 by 3, which I don't really know if you do in this course, but as I haven't seen your exam, right, I'm not leaving anything out.
Yeah. And what's the way you multiply? Is that so you can check what the size of the answer is?
Yeah. Well, because you know here, you expect a single answer, single number, because you're doing 1 minus something, a value. So it has to be a single number.
But like the way you write it, like that.
Yeah,
So
yeah. I'm just doing that so I can just calculate what it is quicker.
Yeah.
Right, like here, I just did that so I could just do 0 times that and that, so I got this number. My working is not always the neatest, I must admit, but
that works well. It always be
yes.
I had like I only had like an in-person exam like last term, so I never bothered to work on
Yeah, yeah. No, that's how I sort of always do it. You just sort of like put it in those positions, and then sometimes you're sort of like, should I have written that extra line down? Nah, it's fine. If you're in a doubt, what you can always do is you can just sort of be like, put on a comment here saying this is like, I don't know, this and this together, something like that. Just to sort of be like, it's only really an issue if you feel like you've gone halfway through the question and you feel like there's a mistake somewhere and you're running out of time. You might put a comment being like, this is what this is. That way, if they start looking for things, they can easily spot what it is. But most of the time, if it helps you get to the workings to the correct answer, it's not really an issue. In terms of what Arash is sort of expecting for a question like this, right? This would be a mark. This would be a mark. Well, he's sort of just got like 2.5 marks for all of this working. So it's not really specific that you need anything, but it's what you need, just working needed to get to the final answer, rather than just jumping going, oh, the answer is 0.2. You'd be like, where did that come from? All right, cool. Any questions with that? Yeah, I can almost guarantee you'll get a question like this. Almost guarantee it. Because I've had one, it's in here, you'll get one too. So just make sure you remember how to go about it. All right, and now the next part is determine the appropriate observer gain matrix L for a critically damped behavior using the same values for alpha from 1.2. This is where it gets a little bit more annoying because C isn't like only one value and the other 0. That's where it gets a little bit more annoying. But that's okay. So the first thing we need to do is we need to pick pole locations. Pole locations. Now, somewhere up here we wrote here, -8. So since we want to be critically damped, we can say S1 or S1, S2 is equal to -80. Happy with that? Because it's just 10 times. Yeah, go ahead. -80. Cool. And then we just want to do the determinant of SI minus A minus LC. Okay, which we know is equal to S plus 80 squared, because we have double bowl there. Okay, and then we're just going to have S0, 0, S minus 0, 1, minus 4, 0, minus L1, L2, and then 2 minus 4, which is just going to get you 2L1 minus 4L1, 2L2 minus 4L2. So you can already see how this is going to become nasty. That's okay. Okay, and then we're going to end up with S plus 2L1 minus 1 plus 4, no, minus, because there's lots of minuses in there. Please let me know at any time if I jump too much in calculations. I'm just thinking jump through some of the stuff and you can sort of verify it in your own time. And then minus becomes plus 4 plus 2L2, and then minus S minus 4L2. Okay, which is then going to become S plus 2L1, S minus 4L2, minus, which is plus, because I'm going to have 1 plus 4L1, 4 plus 2L2. Okay, which is then going to become S squared plus 2L1 minus 4L2 S plus 16L1 plus 2L1, 2L2 plus 4 is equal to your S squared plus 16S plus 6400. Okay, which all it is just a lot of calculations. It's nasty, but so then you'll have 2L1 minus 4L2 is equal to 16, and then 16 plus 2L2 plus 4 is equal to 6400. Okay. And then you basically will just solve simultaneous equations to eventually get L1 is equal to 150.47, and then L2 is equal to 380.94. Happy with that? Yeah, it's just a lot of working. And finally, that's the end of. Is that enough? Did you want to look at that again?
Oh, yeah.
Cool. All right. No worries. That is the end of question 1. And question 2. All right. So consider the block diagram of a feedback control system. Following question showing the working. Find the steady state error of the closed loop when R of S is equal to 1 of S and TD of S is equal to 0, and determine the system type. All right. So how do we go about this question? Perfect. So we can say that we have this system here, this first part, and then we'll deal with this part. So we know that G prime, let this be G prime, is equal to, I'm going to call this G and this H. All right, so it's going to be G on 1 plus GH, which is equal to 100 over S of S plus 5.6, S plus 10, all over 1 plus 100 on S of S plus 5.6, S plus 10, multiplied by K1, KT of S. So then that S will cancel with that S, multiply everything through, and you're going to end up with 100 over, well, this is going to be S of S plus 5.6, S plus 10, plus 100 KTS. Because we just multiplied the top and bottom by that S of S plus 5.6, S plus 10. That makes sense? It's nasty, I know, but there's not much we can do. And then you can collect this S out the front, which then becomes S plus 5.6, S plus 10, plus 100 kg. Rather than that top line. That makes sense? Cool. And now that we have this, our entire transfer function will be, well, we've basically replaced this one block, so now we have this. Right. So it's just going to be 10 G prime on 1 plus 10 G prime. All right, which means I'm going to end up with, since the top of G is 100, so it's going to end up with 1,000 all on S of S plus 5.6, S plus 10, plus 100 KT, plus 1,000. That is my H of S, or H prime, whatever you want to call it. That makes sense? I know it sort of jumped a little bit, but hopefully that makes sense. Now, what type of system is it? Type 1. Perfect. It is type 1. And the reason is pole at origin. Specifically, pole at origin in that path. So here we have pole at origin. Make sense? Okay, so what's E of S equal to then?
The step.
For a step.
0.
0, perfect. All right. I'm not trying to trick you. It's like either 0, infinity, or 1. Those are the sort of 3 options. Yes, and we can see that because if I send in S is equal to 0 here, that becomes 0. We have 1,000 over 1,000, which becomes 1. So therefore, there's a 1-to-1 relationship, and therefore, the error is 0. All right, cool. And yeah, that's pretty much that question. Make sense? All right, cool. Determine the range of the gain KT so the closed loop system is stable. Okay, so we've gone through all of this. We've ended up with this expression. Now, how do we know whether the system is stable or not? Yes, all the poles are on the left half plane. So from there, we sort of have to expand out this guy at the bottom here, okay? And what we end up getting is S cubed plus 15.6 S squared plus 56 plus 100 KT of S plus 1,000. Okay, and now who can tell me what we need to do from here? It is in your lecture notes, but it is not in the notes that I've added because I honestly didn't think it would appear in exam.
What's the question?
So we need to determine what values these are such that they're stable. And I'll give you the hints of A3.
Oh yeah, it's the inequality.
It is indeed.
A3, A1, less than A2, A0 or something.
So as you said, yes, all of these must be greater than 0.
Oh yeah.
And then what's the other condition?
A3, one of them. A3, A1, A0, less than, oh yeah, yeah. Or greater than, I don't know.
It's like it's one of the two. Yeah, I'm pretty sure it's that one. It is that one. Perfect. So from there, we know currently they all are. So the main thing we're going to have is 56 plus 100 KT must be greater than 0, and that 15.6 times 56 plus 100 KT must be greater than 1,000. Okay, and so you end up with this one saying that KT must be greater than minus 0.56 divided by 100, whatever. 0 negative. Okay, hopefully you can still read that. Handwriting is definitely not the best. And then the other one here is KT must be greater than 0.081, okay? And so since this one includes both the regions, that's our final answer. You need both, otherwise it doesn't prove anything. And that's the Ritz-Hurwitz criteria. Really, the only thing you need to remember is each of these must be positive, and that A1, A2 is bigger than A3, A0.
I think technically should only go score for resistance.
Yes. You go to the table thing where it starts alternating between the two. highly doubt you'll get anything above.
Hopefully, yeah.
There you go.
What happens if we do that and we get two conflicting conditions? It just means that
There's no value for KT such that it's stable. Yeah. I cannot read what that comment says. My apologies. Let me. Perfect. Where were you referring to with the A plus?
the denominator is not like actually called the origin.
Oh, you're saying with this here, why, like, it's not necessarily a pole of the origin. If you consider the blocks separately, this block here, well, because if you think about it, we've got this expression, which goes to this form here, we did factor out that S. So the denominator does have an S on the bottom.
So the inequality is type 1.
So this here, this one block here, it has a pole of the origin. And because the forward path has a pole of the origin, then it's a type 1 system. But if it's the entire closed loop has a pole of the origin, it doesn't necessarily mean it's a type 1 system. I'm pretty sure that's what it is. Because we normally will put, like, say, when we try and solve the problem, we put like an integrator with a PID controller. That's in the forward path, and as a result, that will increase the type of the system. But if you put it down the bottom in like the return path, that doesn't necessarily mean that, because it's not integrating the error. Does that make sense? Okay, hopefully that answers your question. And then we want to say find the steady state error of the closed loop due to unit step disturbance. That is when R of S is equal to 0 and TD of S is equal to 1 on S. Okay. Yeah, that's gonna be a lot of work. Oh my word. Do you want me to go through this one or move on? I'll write the key points. So the key points is you need the transfer function in terms of TD. Okay, and then once you have it in terms of TD of S, then you can go about it. Now the good news is we know that this point here is TD. Okay, so TD is essentially just going to be G prime on 1 plus 10 G prime. And then you can just go through, essentially set S is equal to 0, find what the error steady state value is, go through all of that lovely working.
So you just do
Yeah, like
superposition.
Yeah.
RS.
Yeah, because this becomes 0 now, so nothing comes in. That's part of the feedback path. Yeah. Yeah. Or you can go back to the original, which is what Arash did, and it's a lot of working, but already you can jump to like this point here, and then you just do, yeah, the ESS, the limit as S goes to 0. And yeah, that should, or it should be the limit as S goes to 0 of S times 1 on S, which is where the S's cancel out. Yeah, makes sense? Okay, question 3. It always terrifies me when I start the question. It's just 10 marks, doesn't it? For the closed loop system, determine the range of stability for the parameter P. Oh, look at that. There's so much going on, isn't there? All right, when you get a question like this, where do you reckon you start? Yeah, because ideally you want to like, sort of like in the previous question, we broke it into blocks, okay? But the issue comes in, this part feeds back into here. This part feeds into there. So we can't combine that into anything. So we're kind of a bit stuck.
Maybe start writing the output in terms of stuff.
Yeah.
Work backwards.
Yeah, that seems reasonable to me. I'm going to keep going across. And then we have our block here, which I'm going to call GC of S. Block here, which is going to be G of S. Then we have the adder. Oh, we have an adder here as well. And then that goes here, that goes here, that goes here. Plus minus our R of S, R of S, E of S. And then we have 1 on S plus 1. Well, and that's a minus plus, and then a minus. Alright, and you have 1 on S plus P. These are plus and this is plus. You can see my drawing skills as the exam goes on get more and more impressive. So, E of S, or EA of S, I call this EA of S, is equal to just R of S minus, I'm going to say, well, this is U of S minus U of S plus Y of S. Okay? U of S is equal to EA of S times GC of S minus Y of S. And then Y of S is equal to U of S, G of S. That makes sense? Cool. All right, and then we want our final equation to be in terms of what? You want Y of S on R of S. So we have this bottom one here of Y of S is equal to U of S, G of S. So then we can just say, well, Y of S, for now, is equal to G of S multiplied by EA of S times GC of S minus Y of S. Okay. And then Y of S is equal to G of S multiplied by R of S times GC of S. Nope, not like that. R of S minus U of S plus Y of S times GC of S. But hang on, we've hit a problem, haven't we? What problem have I run into? Where I can keep going until you see it more clearly. Perfect. All right, we have this U of S references EA of S. EA of S references U of S. So I subbed in wherever I had U of S here, chugged in this. We've got E of S of this. And whenever I had E of S, I sub in U. And therefore, I'm going to sub in E again. I'm going to sub in U. I'm going to E in U. And so it's never going to end, is it? So the question comes in, how do I solve that problem? Yeah.
How many equations do we have?
We have 3.
Okay, and we want to get 2 variables. And we currently have 4 variables. Oh, yeah. You combine 2 equations to rearrange it to help us look very quickly.
Yep. So I can rearrange that top one to have U of S is equal to R of S minus EA of S plus Y of S. All right, and then we also know that U of S is equal to EA of S times GC of S minus Y of S. And then we can say that EA of S times GC of S minus Y of S is equal to R of S minus EA of S plus Y of S. And now I can do EA of S of GC of S plus 1 is equal to R of S plus minus becomes R of S. So then we can say that, well, that's a bit of an issue. I went through all that work to remove the U of S, but I actually want to remove the,
right. I did the same thing.
the E instead. That's okay. We know that wherever we have, we can sub it back in, and then we can get R of S minus U of S plus Y of S of GC of S plus 1 is equal to R of S. So they cancel out. How cool is that? Well, that's not as good as actually we want, is it?
You want an R of S.
I wanted an R. And the reason for that is because what we'll find is this next line here, it will become, like, because it's minus, so I take these, because that is in here. So I can't cancel them out. We're all good. I'm just going to remove my brackets, because EA of S was multiplied by these two things. Does that make sense? I know it's getting a bit, but it's a 10 marker, right? That's what's going to happen when you get a 10 marker. Okay, and so now we have our U of S. We know that we can replace U of S with Y of S on G of S. So then we're going to have R of S minus Y of S outside of 1 on G of S plus 1. Okay, and then that's going to have a bracket there. GC of S plus 1 is equal to R of S. Okay. That's not the nicest thing, is it? But that's okay. Then we are going to go with Y of S on R of S is going to be, we're going to have this GC of S, G all on 1 plus GC, and then this will be G plus 1. That's what you'll end up with when you expand that horrible thing. Okay, which will then get you 1 on S plus 1, S plus P, all over 1 plus 1 on S plus 1, 1 plus 1 on S plus P, which gets you 1 on S plus 2, S plus P plus 1, and so therefore you'll end up with S squared plus P plus 3S plus 2 lots of P plus 1, and then range of stability. We have 2 of P plus 1 must be greater than 0, so P must be greater than minus 1, and then we have P plus 3 must be greater than 0, so P must be greater than minus 3, and therefore we have that. Long question. But the good news is, although long, it didn't require like very complex remembering of stuff, right? It was just going through the calculations that we've sort of done before, rearranging simultaneous equations, that sort of stuff. Make sense? Okay, so that is question 3.1. Now, I remember him putting this question in there.
Oh, 20.
20 marker. And it was a reference to sensitivity, because they had a reference to it in their projects, which was talking about sensitivity, which is why, although you guys might sit there and go, you covered sensitivity, right?
Yeah, electronics. Yeah.
Have we covered it?
Probably the week 10 lectures are.
Have we covered it in controls yet?
I don't know how much week 10.
Okay.
It's a really good example, so I thought that because I wrote specifically said you weren't needing sensitivity. So I'm guessing sensitivity would be
I hope so too, because you can see 20 marker. The good news is it is like they give you a lot of the stuff for you. Okay, like for this first part, you're just trying to find an SG of T, which is this. First, show that this is that, and you're just going through like normal. But anyway, we'll skip it. Perfect. I'm going back to question 4. I liked question 5, because now we have some short answer stuff, and I feel like I can get you guys more involved with short answer. Okay, so what are the two main issues with the closed loop Ziegler-Nichols technique?
Is that the PID tuning?
It is for PID tuning. Very good.
Does it give you a value to start with for KD and KI?
It gives you a technique that you can use to get those values. Do we remember what Ziegler-Nichols technique is?
was it like matching coefficient and stuff?
Yeah.
Oh,
The main thing it did was I'll give you one of them, one of the reasons, and one of the reasons is it must be third order. Must be third order. Because remembering that is tricky, right? But the thing is, the Ziegler-Nichols technique is a way of designing a PID controller for a system, okay? And what it will do is we will say set the KD and KI to 0. So it'll be set KD equal to 0, KI equal to 0, and now change KP value, okay? And what we're going to do is we're going to have a location of 2 poles. And it uses an approach similar to that of the root locus, which is, yes, we will push these poles until eventually they will get this point here, okay?
I guess the disadvantage is the system might not always be okay with oscillating.
Give me an example of a system that wouldn't be okay with that.
A crane.
A crane.
Won't like it if you do that.
Yeah, very good. The main thing is any real system.
Oh, yeah.
Any real system won't like it. And the main thing because it's dangerous. Mainly because it could lead to breakage, could do anything, right? Because if you get slightly higher, a bit of noise, your system becomes unstable. And can you imagine going to your boss saying, I can design a PID controller for your $1 million plant, but we've got to bring it to the chance that it could break. They'll be like, no. What do you mean? Or it's like an actual robot in delivering parcels or like picking things up and moving it across. It's got to get to the point where it can just basically keep moving back and forth dangerously. Not very good at all. Okay.
So you could do it on a model of the system.
Yes.
Yeah.
Yes. That's why they use it. They use it for models of the system because it's an effective way. right? That way you don't have to worry about all the stuff. But we know heaps of other techniques that you can use. You can use like pole placement strategy, Ackermann's formula, okay? They're all different approaches to put the poles where you want them.
All I know is that actor function.
I thought that was the pole placement. Is active pole placement two different things?
They're two different things.
Oh.
You've used pole placement, and I expect you to know pole placement for the exam. Don't really expect you to know how to use Ackermann's formula. Now, pole placement, the reason why I say that is because pole placement is literally where you go, I want a pole in these two spots to get this percentage overshoot and settling time. And then you set the other ones 10 times far away, you end up with those equations, and what we've been doing earlier, where you then match coefficients. We effectively did it for the K1, K2 values, if you remember. But I don't really expect you to remember the Ackermann's formula, because you're right, you just plug it into MATLAB, and MATLAB tells you what it is. Okay, what useful information can we obtain from the root locus plot of an open loop system about the closed loop behavior of the same system? Provide at least 3 points of information.
Look for sure that it predicts the placement of poles in terms of ECK.
You can see the system's going to become unstable. Like
Perfect.
Yeah.
Determines stability range, yes.
If it looks like it's going to go, like part of the locus is on the right hand side.
There's another one that you should be able to tell me, mainly because I just told you it.
If you can actually place the poles where you want them to go. If it's actually.
Yeah, what did we just answer in the previous question?
Oh, you can find the critical gain.
We pushed to the edge of stability.
Oh yeah.
Right. And what happens when we have here? We have an oscillation. Right. We can know what the oscillation is by being on that critical point. So we can get the frequency of oscillation when using Ziegler-Nichols. What we just had as the question for the previous part is one of the answers here. Does that make sense? So we can use the root locus plot to push it all the way to the edge of stability, and then we will see what frequency it would oscillate at. Which is sort of what you've been telling me. Does that make sense?
Yeah. So you find like the
Yeah, cool.
oscillation frequency.
Yeah, critical or ultimate gain to determine stability. So this is the gain for that. Cool. And what else do we have? The last one is the movement of the closed loop poles and whether or not there will be a gain where the closed loop poles can enter the desired region. So movement of
So
poles.
whether you can actually place the poles where you want.
Yeah. And this also leads to a bit of pole cancellation, pole zero cancellation. All right, like can I move one of my poles to cancel out a zero to make my system even simpler? Does that make sense? Cool. And then 5.3, explain why the PD controller can reduce the overshoot without significantly affecting the speed of the transient response.
Reduce overshoot without affecting speed.
Doesn't induce any.
Well, kind of also to the future, I guess. Like it predicts what the future values are going to be and does that. So.
I love how everyone always uses the predicts the future, because technically it does. I like to think of it as it's quick to respond to changes. Okay, it's more susceptible to noise because it'll act straight away. Okay, if it's a slight change, it goes, we're moving, let's go. Okay, and so the reason that it reduces the overshoot is because as soon as it goes past that point, it goes, I've gone too far, and it's not as slow to respond. Okay, but as a consequence of that, right, like it's quicker to pull itself down, but then the overall time itself doesn't change substantially, because if you increase it massively, it's quicker to bounce around, but the actual time taken for that still remains the same. Okay, which you can sort of see if you look at the equation for it, where you have KBE plus KD E dot, which gets you to be KPE minus KDY. Okay, and so the maximum slope of the set response happens when it reaches very close to the final step value. Therefore, with the derivative term in the control input having the negative sign, that means it reduces the magnitude of the control input as the response reaches close to the final value, which is where it just gets that point where it crosses over and pulls it back down. People are hiding outside. Hello, come on in. This is the crash course, come on in. I'm just going through the 2021 paper. Does that make sense about the KD?
Wait, so how does it do it faster?
See, the important thing is it's not necessarily that it does it faster, but it doesn't make it slower. That's the important thing. So if you look at the response, right, it would go from, say, 0 straight up to this value, right? Then what will happen is it'll go up, and then as soon as it goes beyond, it will start working its way back to that point. Okay, so because that derivative isn't based on previous values, as soon as it goes beyond this point here, it'll start pulling it back down.
Which has to wait for that area to
yes. So if you make the KD value even bigger, right, it will, what can happen is you might end up with a response that looks like this, where it goes up faster and then down and then up and then down and up and down and down. But the actual overall time itself is still relatively the same, right? So that's why it can be used to reduce the overshoot without significantly affecting the speed. Okay, because it might be slower to get to that value, but then the overshoot's less. Or it might be faster to get to that peak value, but it won't settle because it's basically trying to stabilize itself faster. Does that make sense? Okay, then we have question 4. Explain why adding a 0 to the open loop system could be beneficial and where it would be usually placed.
What does that just mean?
What do you mean?
Adding a 0 doesn't have speed.
It does, that's true. That's true. In that case, why did you add the 0? Yes, you're not wrong, but why does that reduce overshoot?
It goes back to where
It is.
where we place the 0 could affect, change the trajectory of where the poles are placed in terms of ECP. Does that make sense? So we could, if the pole is on the right hand side, we could introduce a 0 to move it to the left hand side to stay placed.
How much do we remember of root locus? Is this? Did I skip the root locus? I actually did skip the root locus. That's why we haven't covered it yet. But the main takeaway is if we think of our root locus, right? If I have a system that has, say, 2 poles here, what happens is as I increase the gain, they'll go together. They'll go together before they'll eventually split apart. Okay, but the problem is, right? Like, I may not want that sort of behavior. If what I can do is I can put a 0 here, then what's going to happen is I increase the gain. Right, this one will go away. What happens to this guy?
The right one.
The right one.
So let's just say that.
Well, because that's why we add the zeros, because the whole point of the zeros is it attracts the poles. If there are no zeros, then the poles go at each other and then expand far away. Right, but they have to go somewhere, right?
Isn't the real
Can't just stay
line
there.
axis?
Would it be slightly attracted until the other pole and then cancels out?
And then where would it go?
To the left.
It would actually go to the right, pretty sure. Because it would be repulsed by that other pole. Eventually. So it'd go off to infinity. The good news is, we don't really have to worry about that as much. Right? The trick would be we could have, like, say, a double pole or a double zero. We could track them both that way. Okay? Or we'd have, say, one here and one further away, which would pull one and then pull the other one as well. Because the further away it is, you know, as a result, it gets better for us because our system performs faster. It has no overshoot, which is why the KD works the way it does, because it does pull it. And you must be right. It must be pull it that way. All right. So we've got, according to the root locus, the closed loop will eventually end up at the location of the system zeros. Therefore, adding a zero on the left half plane helps bring the closed loop poles further to the left half plane if the gain is increased, which is stabilizing. And it is recommended that the zero is added to the left side of the first real open loop poles, or at worst case scenario beneath the real part of the closed loop poles. Ah, yes, that's where it comes from. Because if I go back to this, right, let's say I have a single pole. What happens as I increase the gain? It goes not to the right, it goes to the left. It'll go this way. All right, it'll eventually just keep going that way. Which is why, when we have two of them, we like to put the zero here, because then this one will go this way after this one gets there. All right, they'll go that way for a bit, but it'll mainly end up going further to the left. Okay, because we want to cancel out the dominant poles. We don't really want the dominant poles there, because they're too slow.
Hey James, what do you call the little segment between, in this case, between the pole and the zero? What do you call that? Like the real, what's that name? The real,
Real axis.
yeah, that's it.
Yes. Yeah. I'm guessing it's called the real axis. I don't know for certainty. Okay, but those are the two sort of things we're looking for. Alright, so we can sort of cancel out those effects. Alright, and then consider the similarities between the closed loop transfer function of the PD controller of a second order system and a PI controller for a first order system in terms of how the gains affect the damping ratio and natural frequency. Also recall that position control with velocity feedback of a DC motor can make the closed loop system behave exactly like a standard second order system. Using this information, propose a variation of PI controller implementing for a first order system to result in a standard second order closed loop transfer function. Show all your working and explain your approach for this PI implementation. Well, that's a lot of words. What are we thinking, right? Like, did I skip a question? I did skip a question. Okay, explain what would limit the maximum speed of an observer in estimating the state variables.
And you also skip the one above it.
We'll answer 6 first, and then we'll do the other one.
Maximum speed in observer estimating. Well, you can't have everything as fast as you want it because there's only so much energy available.
Perfect. Yep. And also, as soon as you convert it from the S domain back to the frequency domain, you realize, oh, I've just cut off all of these higher frequencies. I now can't send a step input at all. It's now like sinusoidal shape, which is where the problem comes in. But energy is what I like to think of. Why do we usually need to use an observer in state feedback control systems? Explain why it is not always possible to have the accurate estimator of state variables. Yep.
Or you might not even have access to it, like the system might just be like box or whatever.
Yep. Time, cost, and availability. Sometimes it's not even possible. All right, like if I'm making a heart rate monitor, I may not necessarily want to be like, oh no, I need to make sure I check the glucose level of the blood every second, because it might take longer than a second to get that information. All right, and now we have.
I guess as well, like with all those sensors, like you have so many points of failure.
Yes.
If you have sensors measuring every state.
Yep.
And you're relying on all of them to work properly.
Yep, and as soon as one of them doesn't, then it becomes absolute carnage. Okay, all right. What are we thinking for this question? All right, like it's kind of a bit crazy, isn't it?
Oh, this is the lab stuff.
Yeah. Yeah.
I would turn it to dot points and then just skip it.
We have a G of S. Yeah, fair. We have a G of S, right? And then the most important thing here is this is going to be in the form of K of S plus A, right? Because we know it's a first order. We're told it's a first order system. Okay, and then we have this, which we can say is our PI, which is going to be Ki on S. Right. And we gotta do something funky here, which I'm just gonna call it like H. Alright, because we gotta do something to make it different, right? We either put it here or we put it there. And there are two options. Does that make sense? Because they've specifically said it's not a standard one. So either.
The PI controller implementation for first order system, it's
So either H1 or H2 is different.
okay.
Unless you want to start doing feed forward or other stuff like that, which you could do. Well, I don't really think it's what it's just to do. All right, so when it references the lab, it's referencing where in the lab we had the derivative block that we deliberately did not put into the front and instead put it back into the feedback path such that we could have this configuration where we have this as our PID, and then it went KD. That to there. Do you remember that?
So is the topic PI?
The top one could just be P and I. There was no D involved. And the reason for that was because we didn't want to differentiate it when we first sent it in, because it was going to be the difference between the error and not. There's going to be a massive spike, which was causing havoc with our input voltage. Okay. Yeah. So the goal from changing PI and PD is that we want to bring down the overshoot. Okay. And so in order to try and reduce the overshoot, we want to try and figure out a way to limit the value of when we normally would have our omega n squared on S plus 2 zeta omega n S plus omega n squared. Okay. And do we remember which of these two guys affects overshoot the most? Isn't it zeta? Right?
Because zeta's, because OS is proportional to zeta.
Yes.
Highly true.
So we effectively want our Y of S on R of S will equal to this. Okay, it will equal that. We don't have much choice. So we want to somehow modify our expression such that we can make this value here changed. Okay, and so going through from here, where this is a Ki on S, all right, we can either do Kp here, Kp1, or Kp2. Now, which one do you want me to try first, H1 or H2?
Which one's
H1.
easier?
Do that, and then if it works.
All right, because we're going to have the same idea that G prime is equal to G of S on 1 plus G of S H1 of S. That make sense? All right. And then that's just going to be K on S plus A, which I'm going to cancel that and say this is S plus A plus K of Kp. Okay, and then our H of S overall, H prime, is just going to equal Ki on S times G prime all on 1 plus Ki on S times G prime, which leads us to Ki K all on S plus A plus K Kp S plus Ki times K, which then leads us to Ki K on S squared plus S lots of A plus K Kp plus K Ki. And I would say that this here gives me the opportunity to control 2 zeta omega n, and this here gives me control omega n squared. So I can then be able to modify Kp in whatever way that I want, such that I can bring down my overshoot. That make sense?
So it works.
So it works.
Sweet.
And you're probably sitting there going, well, that was a crazy question.
Yeah, when you see like a paragraph or two on the question, when you do, like, what's your kind of, where you tap in?
I think these ones are kind of weird and out there, right? Like a lot of this was sort of like they wanted you to sort of work around the intuitive being like, it might be drawing a couple of pictures so that, for example, like this picture here tells me what a PI or like our implementation difference by putting in that S block here. Okay, so it's giving you the heads up of this is the sort of implementation style that you're looking at, and then you can start doing some working down from it. Does that make sense?
So you kind of draw like a rough sketch of
Yeah.
the system it's describing. And
Yeah.
you kind of match that up, and
Yeah.
you just got to work out what it actually is.
Yeah. Was it an open book? Must have been. I just realized it is recorded. Was this session recorded? Yes, pretty sure it is recorded. Although someone else is recording it. I don't know who is. Someone pressed record. It wasn't me. Okay, so then is there any other questions in there that I missed? Please let me know if I missed anything. Alright, so we have this one here. Consider the closed loop system shown in figure 4 using root locus technique. Find the PID gains. And the reason why I skipped it is because this is a long question. Oh my word. Okay, so the first thing you want to do when you get a question like this is we need the setup information. Okay, what do we actually need? We have a percentage overshoot. All right, and we are told that the percentage overshoot must be less than or equal to 10%, which then allows us to find a zeta value, which is greater than or equal to 0.59. Okay, then we have a peak time, which is less than or equal to 2 seconds, which tells us that omega n must be greater than or equal to 1.947. Okay, so that tells us that the poles of the closed loop system is equal to the minus zeta omega n plus or minus j omega n of 1 minus zeta squared, which is equal to minus 1.15 plus or minus j of 1.57. Happy with that? So that's what I sort of mean by like the first thing you want to do is you want to set up, try and get your closed loop poles, right? Because just by doing this, you can already set up yourself to get to maybe a mark or two, okay? Especially for a bigger question. All right, and then you want to start going, okay, we have our GC of S, which you can't really see here, but I will draw it in quickly again so you can actually see it. Okay, so this is our KP plus KDS plus KI on S, all on 1 on S of S plus 5 squared. Okay, happy with that? And then speed back around, puts it into there, puts it into there, puts it into there. Y of S, R of S plus and minus E of S, U of S, right, and this is G of S, C of S. So you can see quickly why it's handy to have notations, otherwise it's just absolute nightmare. So then GC of S is just going to become KDS squared plus KPS plus KI all on S. And that is going to be equivalent to K of S plus Z1, S plus Z2, all on S. Okay, which if we expand that will be a form of K of S squared plus Z1 plus Z2 plus Z1, Z2, all on S. Okay, that makes sense? Yes, hopefully, cool. So therefore KD is equal to K, KP is equal to K lots of Z1 plus Z2, and then KI is just going to equal to K Z1 and Z2. All right. So that should already be like 2 marks in total, please. Getting all that working done. Okay. Now, we have our G of S, which was at 1 on S of S plus 5 squared. So we can actually just say, well, why don't we just let Z1 equal to 5? Okay, let one of them equal one of the poles to cancel out, so I don't have to worry about it anymore. And that's because we have 3 unknowns, right? 3 unknowns, K, Z1, Z2, and only 2 equations to gain criteria, or from the gain criteria. So we can need to choose one of the zeros arbitrarily, so we chose it just to cancel out one. You could choose any number, and it's fine. Okay, and then we have the angle criterion. Do we remember what this is? I'm gonna be honest, I don't remember. Yeah, that's what I remember. And then you just sort of draw a plot being like, well, we had one here at -5, and then we have to figure out where the other ones are going to go. Or we have 2 at the origin, because we have this one here, and we have this one here. And then we're going to have some 0 along the way, right? Which is going to be Z2. Because we don't have a double pole here anymore, because we cancelled one of them out.
Wait, is the 5, is that a 0 or a pole?
That was a pole and a 0. So it had 2 poles and 1 0. So we cancel one of the poles and zeros, so we're just left with just this single pole.
Okay.
That makes sense?
So wait, that's a double pole on the bottom and then a single pole on the top.
Yes. So we had this G of S was equal to S of S plus 5, right? And then to be multiplied by K of S plus Z1, S plus Z2, on S. So we can see from there. Is that color okay to write in? We're going to go back to black.
Maybe you go
K of S plus Z1, S plus Z2, S squared, S plus 5 all squared. But specifically, don't do that. We set Z1 to be 5. Therefore, that is the same as that. Make sense? So therefore, we only have 1, 0, and 2 poles. No, 3 poles. Apologies, 3 poles. So this is a double. Okay. And from above, we want the poles to be this. So we should have pole at minus 1.15, somewhere like here, whatever, right? So making sure we have this. Right, there's 2 of them going this way. So this can be theater 3, theater 2, theater 1. Make sense? And so therefore we say that of the 0, I'm going to change that to 0, Z0 minus theta of the pole 1 minus pole 2 minus of pole 3 is equal to the 2k plus 1 times 180 degrees. Make sense? Yes. It is a lot of maths. I apologize. So pole 1 is just going to equal 180 minus the tan inverse of 1.57, which is J of 1.57, and then a cross of 1.15, okay, which is going to equal to 126.22 degrees, and then is also equal to 126.22 degrees because it's a double pole. Happy with that? Cool. And then pole 3 is equal to the 180. Well, it's actually not, because we know it's not going to be that angle. Because we can see it's less than 9 degrees. So this is going to be the tan inverse of 1.57 over 5 minus 1.15. Which gets you 22.18 degrees. And then the 0 is just going to be 2k plus 1 times 180 plus 126 plus 126 plus 22, which then gets you, when we set k is equal to -1 to try and cancel some of this stuff out, we end up getting is equal to 94.63 degrees. Bit of trial and error, but eventually you get somewhere in the range where you'll be like, seems appropriate. Happy with that?
So for like a Sunday check, would you just kind of look and be like, oh yeah?
It looked close to 90 degrees, right?
Yeah.
Like,
And if you get like,
if I got 10 degrees, I'd be like, something's not right here.
that's not in the triangle,
Yeah, we would expect it to be somewhere between like, because you know what this angle is. It's just going to be like, just about 54 degrees. So if this is 54, this is 22. You're sitting there going, okay, cool, like, there's only such of an angle that this can be. It is a bit hard, but yeah, a bit of the sanity check is you sit there and go, well, we expect it to be near the middle-ish, right? Because like 1.5 is somewhere between 5 and 0. But like the further it goes up this way, the more it's going to become a smaller angle. The more it comes that way, the bigger the angle it's going to be. It just definitely cannot be bigger than either two of the ends, right? Like, it wouldn't make much sense. Perhaps it is, but I would double check the working before I would confidently say that yes, it is outside those two regions. Make sense? So we've done all of that, and now we want to do, okay, we want to find what the Z2 value actually is, which is then going to be 1.15 minus 1.57 on tan of 94.63 minus, well, it's 180 minus that, so that way it's within that region, because otherwise it's going to be a negative number, which is like 1.023. And that seems reasonable because it's like just on that side, somewhere between the 0 and 5. Happy with that? Cool. And then I'd sit here and go Z2 is basically 1. It's close enough. You don't have to, but you could say it's 1. And then we have the gain criteria, which is going to be K is equal to 1 on the absolute value of GC G of S at the point where S is equal to the minus 1.15 plus J of 1.57. Okay, which is equal to 1 on S plus 5, S plus 1, S squared, S plus 5 squared, so that cancels with that. All right, and we say K, which we sub in all that numbers, and we see it's approximately equal to 10. Okay. This is meant to be G prime, where G prime is just it without the gain. Does that make sense? Because you don't want to include the gain in your substitution because you're solving for the gain. Yes? No? You can say no at any time. I feel like I'm just getting a couple of blank stares. That's okay. I know it's almost the end. Did I rush through that, or is that okay? Okay, perfect. That's fine.
So you chose where to place the 0 just to cancel the whole, right?
Yes.
And then the other 0 you chose with angle criteria.
Yes. So we had 4 poles, and I wanted my final answer to have 2 poles, and I was being able to place 2 zeros wherever I wanted. So I put the first one to cover up exactly where the other pole was, so then I'm only left with 3. Okay. And now the issue is here, I could have placed those 2 poles at the 2 spots to cancel out 2 poles, and I'd be left with only 2 of them. But the issue is, I want my final 2 poles to be in a certain spot. Okay. That was where this criteria came from, right? We were told I want it such that my percentage overshoot is this and my settling time is that. Okay? And so as a result, we first set up here saying that our poles for our closed loop system need to be this. So at the end of the day, I need to essentially get rid of 4 poles and replace them with 2 brand new poles at these spots. Now to do that, I can move 2 of them and then destroy other 2, but in total, those 4 poles can't remain where they are. They need to go. Does that make sense? So, from the PID, right, we essentially are introducing 2 zeros. Okay? So, because we have the ability for this, we have 3 unknowns. We have K, Z1, and Z2. Okay? Now, I will only have 2 equations. I will have my angle criteria and my gain criteria. Now, gain criteria basically will always find you K, whilst your angle criteria will find your location of a 0. Okay? But here's the thing. Because I have 2 of them, I can put those 2 wherever I want, and they would still allow me to reach the certain desired poles. Does that make sense? Right? Like, if I think of this picture here, okay, I could have, and like, I've got a double pole here, another one here. When I go to place my zeros, I'm going to go a different color. I could have one here, one here. I could have, you know, I could go even one here, one here, as long as they met the criteria, all right, of getting to that specific angle. So that becomes the issue. I can put these two poles wherever I want because I will end up with an expression where I have two unknowns to one answer. And then I can change one of them to be whatever I want. Therefore, to make my life easier, right, well, because there was also a double pole here, I was like, well, just, you know what, make life easier, put one of them here. I could choose anywhere, so I just put a location where it cancelled out a pole. And then I was left with 3 poles and 1 0 I could move. Make sense? Yep, okay, cool. And then from there, we were able to use the angle criterion to find an angle, which got us the location of a pole. No, the location of the 0. And then we could use the gain criteria to find the value for the gain. Okay, and now we've done all of that, we can go, well, got to remember that KD was equal to K, which is approximately equal to 10. KP is equal to K of Z1 plus Z2, which is approximately equal to 10 lots of 5 plus 1, which gets you 60. And then KI was equal to K Z1 Z2, which is approximately equal to 10 lots of 5 times 1, which is getting you to 50. Does that make sense? Yep. Okay, cool.
So, I guess the common thing that's going to happen is we're going to forget to do, or what I would forget to do, the KD.
Yes. Please make sure you look back and going, okay, what is it that we're actually going for, right?
The steady state errors, I always calculate like the velocity constant, and I forget to calculate the actual steady state error.
Yeah. I'm not even gonna touch that cable again because it does not like that. Yeah. Across. Which criteria? The angle one is vastly worse than any of the others. The gain, at least, is. Yeah. Up. Now is the time to ask. We've got 10 minutes to the end, so I can answer any questions. Well, I missed the first hour working on the recording for this session. Hopefully it'll be in this channel. Yeah, hopefully it'll be in this channel, and therefore you can go back over through all the stuff. Okay, look, going through this paper, right? I would expect a question, some sort of derived state space. Okay, that's where I would, if I was to put money, I'd say you're going to get something like this. How many marks is it worth? Probably not too many. Okay. What you'll find is it can be first a little bit tricky getting the A, B, and C matrix. Once you have an A, B, and C matrix, most of the things follow quite nicely from it. Chances are you will have to design a state feedback controller. I know we've done it in the project, but it's the staple, right, of finding values for K1 and K2. Now, it most likely will be relatively straightforward, depending on how many marks it's going to be worth. Okay. Yeah, and so going from there, you can then go use the values, right? Like they try and make it up a little bit harder. Okay. But most of the time, as you can see from here, it's just a lot of working. Check the controllability matrix, observability matrix, and then deriving all the information that you need.
So it'll definitely be like a state space question.
Yes.
That would go through. state feedback, and then
Observer.
observer and all that.
Yeah, that's what I expect. I'd be very surprised if there isn't. Yeah, that's what I expect. Okay, then question 2. Yeah, there's probably going to be a steady state error one. Wouldn't surprise me at all. That's just making sure you check the understanding of the definition of it. There will also be a question on stability, wherever the stability is. Yep, like this one here. It may not necessarily be as nasty as this one, because this one's quite nasty, but you will have a question on stability. And you will also have a question on root locus. Okay, and I know it's not always the funnest question to do, but the good news is, if you see from here, it's worth 10 marks. Okay, and since it's pretty much guaranteed almost that it's going to be in there, right? You just want to be thinking, okay, I'll do a couple of practice ones, and I know I'll have to how to do the angle criteria, and whatnot, and even looking at like rough mark indication of where things would be coming from. Right, you get some marks for getting the poles that you need at the very end. Okay, you get marks for understanding that you'll end up with this equation here of KD, KP, KI. Okay, that's what we're trying to solve for. Okay, and then figuring out to use Z is equal to 1 is a bit tricky, but that's what you want to be thinking. I want to find 2 things. K will be basically gain criteria, so it's never going to be that. It's going to be, chances are you set a pole to be something and you find out the pole. Okay. And then you just go through the angle criteria, and the angle criteria is nasty. Okay, so always be careful of that. Yeah. This is probably the hardest section, in my personal opinion, right? Understanding questions, because Arash will ask some crazy stuff that you'll sit there and go,
So it's almost guaranteed that we'll get short answer questions.
yeah, I didn't have any short answer when I did the exam, which I was like, thank heavens for that. I don't know how it's a way.
Like, yeah, if it's a closed book, right?
Yeah, that way
I
it's
mean, you can't just look it up.
exactly.
Yeah.
Because this was all open book, and you're sort of sitting there going, yeah, you could just go explain why adding a 0 could be beneficial and where it should be usually placed. You Google it, and you'll get some sort of answer. Yes. Will the OneNote page for the full solution be posted anywhere as well? Maybe. Maybe it'll be posted. We shall see. I don't know if Arash will release full solutions from past papers. I don't know. Maybe he will. It may not happen until closer to the exam date. I don't know. But at least you can go through all of this stuff to sort of see my working and see my scribbles everywhere. But yeah, there's probably a good chance that it will be released. You'll only release final solutions, no working out. Okay, well, at least you have some working out. Yeah, any other questions or queries for me while I'm here?
Very basic one. It's just like the difference between steady state and transient. Steady state error and transient. There's 2 types of errors, right? There's 2 types of responses. There's the steady state response, which you usually solve with rules and that. And then there's the transient response, which you usually solve with derivatives and that.
I think integrals, like, is that a lead or a lag?
I don't remember. I know exactly what you're referring to, and I put it in those notes.
I'm gonna go with lag.
Yeah, because it would be slower. That would make sense to me. Because if you integrate it, you need to take time to accumulate.
Yeah, so if you're worried about steady state, you look at integral control. Yeah, because it takes a while, but it gets rid of all that area.
Yeah, that makes sense.
And then, yeah, your derivative will be advanced and transient.
Sweet, thanks.
That's intuitive.
That's
LQR the exam.
Extremely unlikely. Okay, because
There's a
I
question, it's like, what's the LQR.
That could be it, right? It could be what is the point at LQR. But like, even when you think about it, if you did the bonus in the lab 6, right, you would find a Q and R matrix, and then you would plug it into some formula that did it all for you, like a MATLAB function LQR. We never got you to actually do the handwriting for it. So perhaps an understanding question could be on it, but like,
Yeah, probably be something about like optimizing it.
the solution you'd say is it's a type of controller design used specifically to optimize and reward particular states or penalize states. Done. All right, like if he made it a 10 marker, that's crazy. I'd sit there and go, I'll go somewhere else. I'll get marks from a different section. That's some of the benefits of having those 12 additional bonus mark things is you can choose questions to be like, you know what, I don't remember this, or I'm not so clear on this, I'll do something else instead. Okay, so I wouldn't panic about LQR. It wasn't in my exam, it's not in this one.
Probably be like, yeah, 2 mark on this day.
Yeah, maybe a 2 marker at best, right? Like, in which case you sort of put down something about optimality and you're like, maybe get a mark.
Just weightings and
Yeah.
they're pretty optimized.
Yeah. But yeah, otherwise, I think that's about it.
Sweet. Thank you so much.
No worries. Thank you all for coming.
Thanks, James.
I hope you all found this useful.
Yep.
I'm gonna steal this. Bring it back. There we go.
Is there a hurdle requirement?
Yes, there are 2 hurdle requirements. 3. First one.